Hello everyone, welcome back to Fluid Mechanics 2. In this module, we're going to learn about what is major and minor losses in pipe. So this is the continuations of the previous material when we talk about viscous flow in pipe. So after discussion about pressure drop, in this module, we'll continue or we'll talk more detail about it, especially how to calculate major and minor losses in pi. So let's talk about major losses. So what is major losses in pi? So it is losses that happen because of frictions in fully developed pipe flow, and it's expressed as these equations. We call it as HF, which is major losses. So from this equation, you can see that major losses are really related with a friction factor, which is what we call Darcy friction factor, F, and then the length of the pipe, the diameter of the pipe, mean flow velocity, V, and last one, gravitational acceleration, or G. So these equations uh, will be happen, or we can use these equations in this case. I mean, it is a pipe flow, or normally you can also express this as a closed channel case. So in closed channel case, we can see that if we measure two pressures in two positions, first at the position 1 and the second at the position 2. In closed channel or in pipe flow, we will get that pressure 1 is not has the same value with pressure 2, and it is different when we talk about open channel, like maybe river or something like that, when pressure 1 will be equal to pressure 2, which is what we call in this case is atmospheric pressure. So that's why these equations is something that we can use in pipe flow or closed channels. And then to measure the difference of the pressure, or normally we call it pressure drop, we need to calculate the pressure loss or the head loss with these equations. Like what I said before, when we talk about major loss, the most important thing to know it is about the friction factor here. And when we talk about friction factor, the thing that we need to find first, it is whether the flow laminar or turbulence, because when we talk about laminar flow, we don't actually need to know about whether the pipe it's rough or smooth. But in turbulent flow, we need to know actually the surface of the wall of the pipe. Okay, so for laminar flow, first let's talk about how to find the friction factor. So we can use these equations, or it will be similar if we use this diagram. So it is 64 divided by Reynolds number. So when you calculate, after you calculate the Reynolds number and you find that the flow is laminar, so you directly can use these equations without knowing whether the pipe is smooth or rough. But if you find that the Reynolds number is turbulence, you need to know these two things. For the rough pipe, we can use Moody chart diagram. You can also use Colebrook equations, and the last one we can use Hallam equations. But if the surface of the pipe is smooth like this, you can see here, you can also directly use these equations to find F or friction factor. But normally, in almost all the case in industry, we use actually these three things to find friction factor: Modi chart diagram, Colebrook equations, and Hallam equations. We're going to talk about it later, but I think you need to be familiar with these three different things. So let's talk about turbulent flow in rough pipe. Like what I said, if you talk about the rough pipe, we have three different things to or different method to calculate or to find the friction factor. First, we need to know about the pipe roughness. It refers to the small irregularities of texture on the inner surface of a pipe that affect fluid frictions and pressure loss. These roughness elements vary depending on the material and manufacturing process. So if you need to know about the roughness of the pipe, actually there are a lot of references that from the book that you can get, like what I show you here. So, for example, if the pipe that you use is concrete, so the equivalent roughness will be 0.3 into 3.0 millimeters. Or if you use feet, so it will be similar with this. Or for example, you use cast iron, the material of your pipe. So the roughness will be equal to 0.26. So this table is something that you need to know. Maybe in some references it's more you can find more type of pipe, the material and manufacturing process, but in these situations or in this course, you only need this table to know the roughness of the pipe. So this is the Moody diagram. This is the diagram that we use to find the friction factor based on Reynolds number and also the roughness of the pipe. I will show you how to use this diagram to find friction factor. The first thing that you need to do, find the Reynolds number. For example, if we get the Reynolds number based on the velocity, the diameter of the part, the viscosity, and the density of the flow, the density of the fluid. So we get, for example, this Reynolds number. It is 8. 80,000. Okay, and then this is where you can see from this diagram. So for example, this is Reynolds number. Okay, since we have this Reynolds number, so we can use the line at these positions. Okay, this is the Reynolds number line, and then the second step that we need to do to find the friction factor using multi-diagram is find the relative roughness. So the relative roughness is actually you need to divide the roughness of the pipe divided by the diameter of the pipe. In this case, we have the relative roughness 0.003. It's an example first. Then, like Reynolds number, what we need to do, we put this relative roughness into this side. This is the example, and then we draw the line. Actually, it should be similar with 0.004 or 0.002, which is the line nearest into this relative roughness. And then the last thing that we need to do to find the friction factor. Okay, I will show you. So since you have drawn the line of the Reynolds number and the relative roughness, when these two lines meet, you need to draw the last line into this friction factor like this. Okay, so this is actually the friction factor of your case where the Reynolds number 80,000 and the relative roughness 0.003. Okay, so this is the positions of the friction factor. It is between 0.025 and 0.03. So the thing that you need to do is use interpolation technique to find the exact value. For example, here, maybe since in this diagram we only have a 0.04 or 0.002, so we need to interpolate the positions of 0.003. Also, sometimes you'll have that the Reynolds number is not 8 or 6, maybe it is just like 63,000, maybe 62, so it will be here. So what you need to do is you need to interpolate to find the exact positions of the line. Okay, also in here, in this case, you need to interpolate to know the exact value of the friction factor. It's between 0.03 and 0.025. Okay, and other options to find or to calculate the friction factor, we can use Kohlberg formula and also Haaland formula. Okay, what's the difference between these two formulas? So first, if you talk about the type, actually multi-diagram is graphical, like what I have explained before. Kohlberg, it is implicit formula. Why it is implicit? Because actually you can see from these equations or formula, on the left side we have friction factor, but also we have friction factor on the right side. That's why it is implicit formula. So we need to do trial and error to find the F or the friction factor actually. But Hallan formula, it is explicit formula since we only have f at the on the left side, so we don't need to do iterations or trial and error calculations. That's why we use explicit formula. If you talk about the accuracy of these three methods, Moody diagram is very accurate. Holbrook very high the accuracy, but Hallan it is good, not bad actually, but not as accurate as Moody and Holbrook method. Moody diagram don't need iterations. Holbrook, like what I have explained, we need iterations. Hallan we don't need iterations. So Moody diagram it is moderate. If we talk about the ease of use, Holbrook is also moderate. Hallan, if even though is less accurate compared to other method, but it is the easiest method to be used to calculate the friction factor. So you can choose which one do you uh, do you use to calculate the friction factor. Also, you can maybe use other method to to compare the friction factor to validate the friction factor. Okay, for example, you choose Hallan formula, and because you are afraid that it is not really accurate, then you compare the result into Moody diagram. Then until you feel that the friction factor is validated. So you can use these three methods. Okay.